As you get ready to listen to this video, please make sure that you have printed out the PowerPoint slides for section 10.4, part 1, so that you can take notes as we go through the PowerPoint here. We are going to focus on what's known as the sum and difference formulas, and there are basically 6 different formulas for this. There's a formula when we are adding the sine of 2 angles, when we're subtracting the sine of 2 angles, when we're adding the cosine of 2 angles, when we're subtracting the cosine of 2 angles, when we're adding the tangent of 2 angles, and we're subtracting the tangent of 2 angles. And the reason we have all these formulas is because sine, cosine, and tangent are not distributive. And so we have to use a formula instead. And these are all written on your note sheets, so you can just refer back to your trig cheat sheet to under sum and difference formula. So that's what these are labeled. Now, on your note sheet, to save paper, I'm going to use tangent because I have a little bit more room. They wrote it as tangent plus or minus, and then the plus sign that's on top is going to be the top when you read it in your formula. So like there's a plus and a minus in the numerator, but then there's a minus and a plus in the denominator. And so that's how we follow through which one is being added and which one is being subtracted in all of these different formulas. So in these first couple examples, we're just figuring out which formula, whether it's a sine addition, a cosine subtraction, or a tangent addition or subtraction. And so it's written much more nicely on your paper. And instead of, cosine of 1,000, it's cosine of 100 degrees. And we have cosine, cosine plus sine, sine. So cosine, cosine is for the cosine formula, and then with a plus in there, it's actually the cosine subtraction formula. And so we are going to take cosine of 100 and subtract 80. And so we wind up with cosine of 20 degrees. This doesn't always work. Sometimes we're literally using the letters A and B when we're talking about identities that are coming our way. In number 2, we have sine, cosine, cosine, sine. So that is a sine pattern, and when it has subtraction with sine, that is truly a sine subtraction of 2 angles. And so we're going to say that this is sine of pi over 3 minus pi over 6. And since those are 2 radians, I can subtract pi over 3 and pi over 6. I just need a common denominator. And so I need to get both of them into the denominator of 6. So that would be sine of 2 pi over 6 minus pi over 6, which would ultimately give us the sine of pi over 6 as our final. So in this question, we're trying to figure out for 75 degrees, so that exciting noise was the fire drill going off in the math lab. And after a day's break, let's get back to finding the exact value for the sine of 75 degrees. So when you're talking about exact value, we want to find the angles where we know values from the unit circle. So we're thinking 30, 45, 60, maybe 90 if we need larger values. And we're trying to find ways to add or subtract to get to 75. And so we can pretty quickly realize that 30 plus 45 gives us 75 degrees, which means that this is a sign of addition situation. So we are rewriting this as the sine of 30 plus 45, and then we will have to use our sine addition formula to be able to evaluate the sine of 75. So my first angle, 30, is going to be the alpha in the formula, and 45 is going to be my beta. So I have sine 30 cosine 45 plus cosine 30 sine 45. And I know that 45-degree angles give me the square root of 2 over 2. And the only one I have memorized is the sine of 30 as 1/2. And the cosine of 30 must then be the square root of 3 over 2. And I am multiplying the sine cosine. So I'm going to have the square root of 2 over 4 plus the square root, let's see, when I'm multiplying square roots, little aside, I have one square root, square root of 3 times the square root of 2. I can multiply those underneath the square root sign together, so I would get the square root of 6 over 4 when we actually multiply the denominators together. And now I have a common denominator, but the square root of 2 and the square root of 6 are not like terms, so I have to leave them as separate square roots in the numerator. It helps if you actually write what we have. So the sine of 75 is this gorgeous fraction. So finding similar exact values, if we have 15 degrees, we can find 15 degrees a couple of different ways. We could do 45 minus 30, we could do 60 minus 45, but in this case, I decided to take 45 minus 30, and with our cosine formula, that means we do cosine cosine plus sine sine, and we know that 45 degrees gives us the square root of 2 over 2, and sine of 30 I have memorized, so the cosine of 30 must be the square root of 3 over 2. And this is looking awfully similar to what we just did, square root of 6 over 4 plus the square root of 2 over 4. So the cosine of 15 equals the same thing as the cosine of 75, which happens to hold true if we look at any cosine value and sine value that together add to 90 degrees. They are the same value. Now, your next favorite, looking at 5 pi over 12, we're going to have to break that down into some radians. So the ones we know on the unit circle would be pi over 3, pi over 4, and pi over 6. So I'm looking to see which of those two either add or subtract to give me 5 pi over 12. And it looks like it would be pi over 4 and pi over 6. So I'm looking at an addition formula of pi over 4 plus pi over 6. And then sine addition means that I go sine and then cosine of the second plus the sine of the second cosine of the first. And incidentally, the reason that we're using these sine and cosine addition formulas is because sine is not distributive. I have to use this whole other formula if I want to add two angles together using sine. Alright, so at pi over 4, I get the square root of 2 over 2. Same thing with cosine. And pi over 6 is the only one that I have memorized. And I think we've seen this answer once or twice before. So some of these answers, they kind of start getting familiar after you've done them once or twice. So now we're going to look at starting to verify some of our identities. And in this we have a cosine addition. So I am going to use my cosine addition formula, and that tells me that I need cosine pi over 2 and then cosine of the second minus sine of the first and sine of the second. Well, cosine at pi over 2, that's going to be my x value at 90 degrees. And my x value at 90 degrees might be 0. So I'm taking 0 times something, which is going to cancel very nicely to nothing. Then I'm looking at the sine at 90 degrees, and that's my y value at 90. That might be known as 1. So if I have negative 1 times sine, that's called negative sine theta, and that equals negative sine theta, and that's exactly what I wanted. So in this one, we have some information about the ratio of the sides of my triangle, and some information here about the quadrant, and this is in quadrant 1. So when I draw my nice triangle, I have my adjacent and my hypotenuse, and that must be my opposite. So cosine addition gives me cosine, cosine, minus sine, sine. So I know my cosine because they indicated that. And let's see, at pi over 6. Now sine of theta, I have to go look at my triangle. And sine of pi over 6. And now if I multiply my fractions together, and then I'd have 4 over 10. I now have two fractions that are the same denominator. So cosine of theta plus pi over 6 equals 3 square root of 3 minus 4 divided by 10. Okay, so this is telling me that A and B are acute angles, which means they have to be less than 90, so they both have to be in the first quadrant. So So I'm going to draw a couple of triangles. One represent angle A, the other one representing angle B. So angle A tells me my opposite is 2 and my hypotenuse is 3. And if I do a little Pythagorean theorem, 9 minus 4 equals 5. So this must be the square root of 5. In B, my cosine, so I have 4 and 5, and my missing side must be 3. Okay, then looking for sine of A plus B, I know that's sine A cosine B, cosine A sine B. So without even drawing my triangles, I had sine A and cosine B, but I definitely need my triangles to get the other two. The cosine of A is adjacent over hypotenuse from my A triangle, and the sine of B is opposite over hypotenuse in the second triangle for B. So that would give me 8 over 15 plus 3 square root of 5 over 15. And I have a common denominator. And that must be the sine of A plus B. Now there's a couple of identities that are known as double angle identities. And we're looking at how they come about. So if I have the sine of alpha plus alpha, I'm using my addition formula, which lets me take the sine of alpha, cosine of alpha, and add the sine of alpha, not plus, times the cosine of alpha. So this is literally getting 2 of the sine alpha cosine alpha. And so that's where our identity for a double angle comes from with sine. And I'm going to do the exact same reasoning to get a double angle for cosine using my cosine setup. I would have cosine A times cosine A, and it's addition, so I'm subtracting sine A, and cosine times cosine is called cosine squared, and sine squared. So that's the first identity that comes up. So in this double angle formula, again, I have just one option for changing the sign of 2x. I can only look at 2 sine x cosine x. In the denominator, I have different options for cosine 2x. And so, since it starts with 1 plus, I would really like to use my replacement to have a minus 1. And so I have 2 cosine squared minus 1. And that's going to help a lot. I don't need to distribute any negatives this time. I can just take 1 plus and 1 minus. They will cancel. Then positive 2 divided by 2, and then a cosine and a cosine squared. So all I'm left with is sine over cosine, and that is a tangent equaling a tangent. Okay, so when I look at this, I don't exactly have any double angles that I need to eliminate. I see some tangents, and I see a tangent squared. So a tangent squared makes me think that maybe I have a Pythagorean identity. So when I check out my Pythagorean identities, I see tangent squared plus 1 is secant squared, and that's basically what I have in the denominator there. So I'm going to replace with secant squared and see if that helps me. Because I've now started making my fraction simpler. I now have a single fraction over a single fraction. I am going to make it a little more complicated because tangent and secant don't have anything that will cancel. I'm going to start by turning things into sine and cosine. And if you're wondering where the 2 goes, it goes in the numerator. And secant is 1 over cosine. So now that I have a fraction divided by a fraction, I can multiply by the reciprocal. And I have cosine in the denominator and cosine squared in the numerator, so I can cancel one of those. So I have 2 sine cosine x. And if you would like, you could take your sine 2x and make that 2 sine x cosine x, so that you now have exactly the same thing on both sides. And stop there. Or if you recognize 2 sine x cosine x as the sine of 2x, and you want to make that equal the sine of 2x, you can do that and stop at either place.